For years, training massive large language models has been, well, a high-stakes battle against instability.
Absolutely. The second you try to scale up, the internal computations just tend to run away.
Right, what we call exploding activations. It forces engineers to rely on these really frustrating architectural patches.
Well, today on AI Paper Podcast, we're looking at controlled LLM training on Spectral Sphere. This paper introduces the Spectral Sphere Optimizer, or SSO, and it just flips the script entirely.
How so?
Instead of just patching the instability, SSO treats it as a fundamental geometric problem that you can actually solve from the ground up.
So the key insight here is that the existing advanced optimizers, something like Muon, are really only half aligned with the stability rules of Maximal Update Parametrization, or BPL.
Exactly. They constrain how far the parameters update, but they let the weights themselves just drift all over the place.
And that's the problem.
That's the problem. SSO fixes this. It identifies something called the spectral sphere, the space where features are learned most stably, and it imposes strict geometric constraints on both the weights and the updates.
It's like the difference between trying to steer a car with a loose wheel versus, rebuilding the whole steering column.
A perfect analogy. And the results. They speak for themselves.
Okay, so what are we talking about?
Across a whole range of models, a dense 1.7 billion LLM, an 8 billion parameter mixture of experts SSO consistently beats AdamW and Muon.
It gives you stability benefits you just don't see otherwise, right? Like strictly bounded activations, no more attention logic outliers, and much better load balancing in MOE routers.
And here's the kicker, the ultimate validation for anyone who cares about scaling laws. SSO is the only optimizer they tested that truly preserves that stable MEPLT learning rate transfer across a huge range of model widths. The math finally holds up in practice.
Okay, so let's unpack that core concept, stability. We hear the term maximal update parametrization thrown around a lot, but for those of us who aren't deep in scaling theory, what's its real mission mathematically? Why is it the benchmark?
So MAPP is basically the mathematical safeguard that lets you scale LLMs wider without the training just completely diverging.
Okay.
Its core requirement is, in concept, pretty simple. As you change the width of the network, the magnitude of your layer activations has to stay invariant.
It has to stay at a scale of theta.
Exactly.
Yeah.
If your activations double every single layer, you're going to hit an explosion and poof, your training signal just vanishes.
And to get that scale invariance, MEPP puts a very specific spectral condition on the weights.
That's the heart of it. The math says that the spectral norm, which for a weight matrix is just the size of its biggest singular value of both the weights, dollars, and the update, has to scale in a very specific way.
As the scale.
Precisely.
Yeah.
That scaling law is the fundamental thing that protects you from runaway growth.
So if that's the golden rule, why have all these other sophisticated methods failed to enforce it perfectly? Let's take the standard approach first, decoupled weight decay.
Well, weight decay is what we'd call a soft regularization. It's gently trying to nudge the weights back towards zero.
Just a little nudge.
Just a nudge. But the paper points out that over these super long training runs we use for LLMs, that soft nudge is just, it's not enough. It's like trying to stop a tidal wave with a leaky bucket.
So the weights just drift off that ideal Monpy spectral scale over time.
And that degrades your feature learning and eventually causes instability.
Okay, so then we got Muon, which was a huge step forward. It's often seen as the steepest descent under the spectral norm, so it's incredibly efficient.
It is.
So what's the fatal flaw? Why is it only half aligned?
Muon is brilliant because it constrains the update direction, the spectral aid. It makes sure you take the fastest path downhill in that spectral space. But you just hit on the key failure point.
The weights.
The weights themselves are still unconstrained. They are completely free to drift and scale, even if the step you're taking is technically the most efficient one.
Wait, I'm not sure I follow. Why does that weight drift matter so much if the updates are already constrained? Why do the weights have to stay put?
Because the entire stability of your network hinges on the hidden states remaining constant in magnitude. If the magnitude of your weight matrix $, grows beyond that UP target,
the output of that layer is guaranteed to explode?
Guaranteed. It destabilizes all the downstream hidden states. And this is precisely why, even with an optimizer as good as Muon, you see people adding all these ad hoc architectural patches.
Things like sandwich norm, QK norm, legit soft capping.
All of them. They're all designed to artificially clip or normalize the activations after the fact.
And those patches are messy. They need extra hyperparameter tuning, and sometimes you're actually sacrificing model expressivity just to force it to be stable.
Exactly. So it sounds like the authors realized they couldn't just constrain the step. They had to police the terrain itself.
A truly stable optimization process should feel seamless, right? Not require a bunch of duct tape layered onto the architecture.
That's the goal. So this led the authors to ask a really fundamental question. Can we simultaneously get the fastest convergence, that steepest descent property, and enforce the strict orthopy constraints for stability?
So turning that ideal spectral scale into a hard boundary.
A hard boundary, not a suggestion.
Yeah.
And their answer is yes, by identifying the spectral sphere as the natural geometric home for stable feature learning.
Okay, so SSO unifies these two things, stability and convergence, by defining the optimization as steepest descent, but with a catch.
A huge catch. It constrains both the weights, $2 saying, and the unit update fillers to the specific sphere defined by the target nodal radius, which they call Brenner.
This is where the geometric innovation really comes in then.
It is. Imagine you're walking on the surface of a giant basketball. Your goal is to take the steepest step downhill, but you are absolutely forbidden from piercing the surface or jumping off it.
Which means your update direction has to be tangent to the sphere.
Perfectly tangent. So, to make sure the weight norm stays constant after you take a step, that the radius of your sphere doesn't change, the first-order Taylor approximation term has to vanish.
Okay, walk us through that concept without just reciting the math.
Conceptually, it just means the update direction theta has to be perfectly perpendicular to the direction of maximum change in the weights, $2. If you think of a vector, theta, that points straight out from the sphere's surface.
Derived from the principal singular vectors.
Right. Then the update direction fillet has to be orthogonal to it. They can't point in the same direction at all.
And they use this Lagrange multiplier search, the Lambda search, to solve for that perfect tangential direction. It's basically finding the one update that balances speed and constraint.
Correct. The Lambda search finds the unique root lambda that makes sure that orthogonality constraint is met. Once they have that, they can calculate the perfect steepest descent direction using a standard operation called the matrix sign function, or M sign.
That sounds incredibly computationally intensive. But the paper makes a big deal about how tractable this solver is.
And that's the beauty of the theory they're applying here. They proved that the function they use to find the root is monotonically non-decreasing, and the solution is strictly bounded.
So they know where to look for it.
They know exactly where to start looking for lambda. And that makes the iterative solver, which uses bracketing followed by bisection, surprisingly fast and reliable. It's not some wild, unconstrained search.
Okay, so that's the first order constraint, the tangent step. But even the best tangential step can cause a little bit of drift over millions of iterations. You've got to keep the weights rigorously on that sphere. How do they handle that secondary correction?
That's the second order constraint, which they call the retraction step. It's simple, but it's absolutely crucial.
What does it do?
Every single step, they just project the weights dollars back onto the manifold. They literally enforce dollars becomes $1 divided by the norm of dollar.
That strictly enforces that the spectral norm of dollars is always equal to the target radius, $3, for the entire training run.
Always.
Wow. That's huge. That completely changes the role of conventional regularization then.
It does.
Because if the spectral norm is strictly policed, weight decay, which is mostly there to limit the weight scale and is notoriously hard to tune, just becomes redundant for these hidden 2D weights.
Completely redundant. SSO eliminates a major super-sensitive hyperparameter. It simplifies the whole tuning process dramatically. They swapped a messy heuristic for a fundamental geometric constraint. It's a massive cleanup. But, you know, this mathematical elegance runs headfirst into the messy reality of large-scale LLM infrastructure. Implementing an iterative root finder on billions of parameters is a serious engineering challenge.
That's the core trade-off, right? You enforce this strict geometry using the Lambda search, but it introduces overhead. The search is iterative, and it needs frequent synchronization between the GPU and the CPU. So how did they build a pipeline that could actually handle that cost?
They had to be extremely clever about it. First, they looked at the core parameters, like the spectral radius scale, $2.
Right.
That dollars is defined by a constant times the no-part scaling factor. And that constant dollar essentially controls the signal-to-noise ratio in the residual path.
And the ablation studies they ran showed that a moderate scale, like $2, gave the best performance. So you need a little bit of a buffer in the signal magnitude.
Precisely. Next, they looked at the learning rate scalar that's used to define tree dollars. They tested 3 popular options, and the results just screamed validation for the spectral move-talk scalar.
So that confirms that if you're going to optimize on a spectral manifold, you have to use a scalar that's explicitly calibrated to the spectral norm. The old AdamW and K-mean heuristics just don't cut it.
They fell short. And then there's this implementation detail that actually saved a ton of performance, atomic sharding.
Right. Modern LLMs are efficient because they fuse weight matrices like the Q, K, and V tensors in attention into one big physical tensor.
But imposing one single unified constraint on a fused tensor like that is suboptimal. The Q, K, and V components have really distinct functional roles.
So SSO needs what they call atomic module sharding.
Yes. Treating the minimal independent weight matrix as the unit of optimization. They found that just splitting the QKV matrix per attention head gave the biggest performance gain. It confirms that you need that fine-grained geometric control.
And that sharding strategy immediately conflicts with standard methods like 0-1, which uses flat buffer sharding.
That's right. They couldn't rely on the standard toolbox. And the Lambda search created another headache. Workload imbalance.
Oh, because some modules converge their search quickly and others take more iterations.
Exactly. And if you process them sequentially, your whole pipeline is waiting on the slowest one.
So they came up with that ping-pong load balancing strategy.
It's a surprisingly simple heuristic, but it's really effective. They just sort the modules by size and then assign them to processing streams in an alternating zigzag pattern. It manages the variable solver depths without needing complex, slow runtime scheduling.
And for the heavy lifting, the matrix sign function computation, they customized the kernels.
Yeah, they implemented an adaptive dispatcher, JIT compiled PyTorch for the small matrices, and a custom Triton SYRK kernel for the big ones.
Smart.
And 2 final tricks. They used multi-stream parallelism for layers with lots of small independent matrices, and this is a big one, they cached the top singular vectors from the previous step.
So caching those vectors speeds up the power iteration convergence. That's the method they used to find the vectors in the first place.
Right, which is critical for setting up the tangent space for the next step. And all this engineering effort really mattered. The final optimized pipeline cut latency by almost 30% compared to a naive baseline.
So the SSO step is still a bit slower than Muon, what, about 11.5%?
It is. But that's a cost the authors argue is absolutely worth paying for the stability premium you get in return.
Okay, let's ground all this in the real-world results, starting with the dense 1.7 billion parameter model. How did SSO actually fare against the incumbents?
Well, SSO showed pure efficiency gains here. It reached the target validation loss 19% faster so in fewer training steps than AdamW did.
And that was even though the learning rate sweeps actually favored AdamW.
Exactly. SSO's speed and its inherent stability allow it to just pull ahead in wall clock time and achieve the highest average downstream benchmark accuracy.
But the real stress test for stability, that has to be the mixture of experts model, the MOE. Those architectures are just notoriously tricky.
They are. Routing decisions can be highly unstable. They tested this on a MOE model with 8 billion parameters.
And this is where SSO really came into its own.
It absolutely shone. It got the lowest validation loss overall, but crucially, it maintained the best expert load balance. We measure that with a metric called maximal violation, or MaxVO.
And for anyone listening, MaxVO basically tells you how unevenly traffic is being sent to the different experts. 0 means perfect balance.
And I remember seeing the graphs for Muon and AdamW that they were just terrible at this. They had these massive MaxVO spikes.
AdamW in particular showed huge spikes, catastrophic routing instability.
SSO, because of its strict spectral control, prevented that runaway growth in the routing layer weights. It promoted balanced routing through the entire process. That geometric constraint is just inherently good for distributing the workload fairly.
They even had to address a small architectural detail in the MOE, didn't they? Something about a magnitude mismatch.
Right, between the main shared experts and the routed experts, which use these tiny sigmoid scores. They used a MOE routing scaling factor of about 2.0 to rebalance that magnitude.
So it shows that stability still needs the architecture to be calibrated, but SSO ensures that calibration actually holds.
Exactly. And finally, the ultimate proof. The DeepNet 200-layer stress test. This is where conventional optimizers usually just die a slow, painful death.
Yeah, extreme depth is a killer.
In this test, AdamW showed really pronounced instability. Frequent, growing loss spikes. The performance gap just got wider and wider over time.
And SSO?
SSO got the lowest loss and the highest stability. It confirmed that this method of rigorously constraining layer magnitude can handle networks where activation control would otherwise be impossible.
And the definitive validation for anyone who cares about scaling laws has to be the width scaling experiment.
This is it. This is the confirmation of full Mickey alignment. SSO was the only optimizer that demonstrated stable, optimal learning rate transfer across a 25x range of model widths.
From 70 million parameters all the way up to 1.8 billion.
All the way up. The optimal learning rate just stayed constant. Muon, which is good, still showed noticeable drift in its optimal LR. It just confirms that half-aligned status still impacts predictable scaling.
So SSO is the first optimizer that seems to fully live up to the promise of attempt.
It really seems to be.
So if we step back and look at the whole picture, SSO provides this mathematically unique solution. It treats stability, those pesky exploding activations, not as something you fix with a patch after the fact.
No, it treats it as a fundamental geometric property of the optimization landscape itself, anchored to this idea of the spectral sphere.
And it's important to point out how this is different from other geometric approaches, right? Like optimization on the Stiefel manifold.
That's a great point. Stiefel is hyper-rigid. It forces all the singular values to be exactly 1. SSO is much more flexible.
It only constrains the maximal singular value to that target radius, $3.
Right. It lets the internal spectrum evolve freely below that ceiling. It's like setting a speed limit without dictating the entire internal roadmap for every car on the highway.
And looking forward, the biggest bottleneck is still that infrastructure cost, isn't it? Specifically, the iterative Lambda search root solver.
Exactly. Future work is going to have to focus on getting rid of that CPU-GPU synchronization overhead. That probably means pure GPU native solvers and moving to higher convergence algorithms, maybe like Brent's method.
They also see SSO's guaranteed stability as the key to unlocking something else.
Reliable, low-precision training. Things like FP8, where small errors usually lead to catastrophic divergence. SSO could make that a lot safer.
You know, this paper really demonstrates that these strict geometric constraints, which we often think of as computationally costly, can actually eliminate the need for heuristic patches. They get rid of sensitive hyperparameters like weight decay.
And that leads to cleaner, more stable, and ultimately more performant large-scale training.
It really raises a fascinating question for everyone working in this space, one for you to mull over. Should we now view any LLM optimization strategy that isn't fully manifold constrained as being, well, fundamentally incomplete?